This is Dr. D. Govardhan, Professor and Dean, Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today we are discussing this overall heat transfer coefficient in heat and mass transfer subject. The conduction process. Conduction is the process of heat transfer. Particularly, it will take in the solids only from higher temperature region to the lower temperature regions. When these two bodies are having direct physical in contact. Here, the heat energy flows generally from the body which is having high temperature to a body lower temperature. That means when the temperature difference that exists, then only heat energy flows through the bodies. Generally, this process is taking place in solids only. The amount of heat energy that is transmitted between the two bodies or one region to the another region of the same body is generally proportional to the thermal conductivity of the materials as well as the temperature difference that exists. Here the amount of heat energy that flows between the two solid bodies when they are in contact or in the same body from one region to the another region can be determined by using Fourier's law. The Fourier's law of conduction states that the heat flow conduction in any direction is proportional to the temperature gradient and the area perpendicular to the flow directions. Here the temperature gradient means the change in temperature per the unit length. Since the heat energy is flowing from higher temperature to lower temperature, that means here the temperature gradient means final temperature is the difference of final temperature to lower temperature. Hence, it is always negative only. So, according to the Fourier's law, the amount of heat energy that flows between the two bodies or from one point to another point in the same body is given by the equations Q is equal to minus of K into A into dt by dx now. Where dt by dx is called the change in temperature per unit length. Generally, it is treated as a temperature gradient. It is always expressed in negative now. Where K is representing the thermal conductivity of the materials, it is always depends upon the property of the materials. A is the cross section of the surface. The units generally used for the heat energy, they are measured in watts only. If the magnitude of heat energy is more, generally it is expressed in kilowatts. And K is the thermal conductivity of the materials. Its value is equal to watts per meter per degree Kelvin. dt by dx is the temperature gradient. Temperature is measured in Kelvin and the distance is measured in meters. Hence, the units of gradient is equal to Kelvin per meter. Basically, the conductivity is represent the flow of heat energy through the materials. The higher value of thermal conductivity is representing large amount of heat energy that flows in that body. When K value is less means that is treated as a bad conductor. It will not allow the flow of heat energy from it. Hence, it will act as an insulator. Okay, based on Fourier's law, we are taking one problem. Determine the heat flow across the wall of 10 centimeter thickness with a constant thermal conductivity of 8.5 watts per meter per degree Kelvin when the surface temperatures are steady at 100 degrees centigrade and 30 degrees centigrade and the wall area is 3 meters. Also find the temperature gradient in the flow directions. Okay, in this problem the given data is the higher temperature of the body is, that is from which the heat energy is flowing, is representing T1 is equal to 100 degrees centigrade, and lower temperature is T2 equal to 30 degrees centigrade. The thickness of the wall is given 10 centimeters, but all dimensions are expressed in MKS units. Hence, convert that 10 centimeters into meters, which is equal to 0.1 meters. The thermal conductivity K is equal to 8.5 watts per meter and Kelvin. Wall area is equal to 3 meters square. Heat flow is equal to the amount of heat energy that flows through the wall is given by the equations K into A into T1 minus T2 divided by L. So from these relations, we got Q is equal to 8.5 into, that is the K values, thermal conductivity is given, into area is equal to 3. T1, T2 is given 100 minus 30 divided by length, that is the thickness of the wall is equal to 0.1. And doing the calculations, we got this value is equal to 17,850 watts. R is also equal to 17.85 kilowatts. The temperature gradient in the flow direction is represented as dt by dx. It is always expressed in negative only. Temperature difference is equal to here now. Maximum is given 100, minimum is 30, and so difference is equal to 70 only, divided by 0.1. That is, we can take it as dt divided by dx is equal to temperature gradient, which is equal to 100 minus 30 divided by 0.1, which is equal to 70 divided by 0.1. R is equal to 700 Kelvin per year meter now. The same values is obtained if the units are converted into Kelvin also now. The same values. And the second one is these values also can be determined by using the relations now. That is Q is equal to, that is the amount of heat energy that is flowing. It is equal to K into A into dt divided by dx. Because already Q values will be determined, which is equal to 17.85 kilowatts, or it is equal to 17,850 divided by K into A. K equal to given 8.5 divided by 3 is nothing but it is equal to 1700 degrees centigrade. So we can use any mathematical relations for determination of temperature gradient. The second problem is determine the heat transfer by convection over a surface of 0.5 meter square area if the surface is at 160 degree centigrade and the fluid is at 40 degree centigrade. The value of convective heat transfer coefficient is 25 watts per meter square per degree Kelvin. Also estimate the temperature gradient at the surface given K equal to 1 watts per meter per degree Kelvin. So first of all, identify what is the given data in the problems. The surface area is given 0.5 meter square. That the area of the cross section is given. The inner temperature is given 160 degree centigrade. Outer temperature is given T2 is equal to 40 degree centigrade. The convective heat transfer coefficient is generally it is represented as H. It is equal to 25 watts per meter per degree Kelvin. Thermal conductivity K equal to 1 watt per meter per degree Kelvin. Hence, heat transfer by the convection is equal to H into A into T1 minus T2 now. where H is equal to convective heat transfer coefficient, A is equal to area of the cross section, T1 is the maximum temperature from which the body is transferring the heat energy to lower temperature T2. So by substituting the values in this equation, we got H is equal to 25, A is equal to 0.5, into T1 minus T2 is equal to 160 minus 40. From this relation, we got 1500 watts, which is equal to 1.5 kilowatts. The heat transfer by the conduction is equal to, here given, minus of K into A dt by dx. From this relationship, we got d2 by dx is equal to, here, the amount of heat energy that is transferring, which is equal to the amount of energy that is received from the convection process. Hence, d2 by dx is equal to, we can take it as minus of q by q into Ka minus of 1500 divided by 1 into 0.5, which is equal to minus of 3000 degree centigrade per meter. Okay, conductions through the composite walls. Till now, just we discussed the problems which are based on the heat transfer that is taking place between the slab or the solid, the inlet temperature as well as the outlet temperature given, and moreover, it is in steady state conditions. That is the amount of heat energy that is flowing per unit time, it remains constant. Here we are taking composite walls now. Here in composite walls, generally the walls it may be made up of more than one layer depending on type of the problems. The heat energy is flowing from this inner surface of the one wall to the outer surface of the other wall, in which the wall is having 2 to 3 layers or 4 layers depending upon this thickness as well as the type of the walls or the slab what we selected. So in that case, the total energy that is flowing from each layer we have to determine. So in most of the cases it is steady state condition only. That is the amount of heat energy flowing through the walls remains constant, but the temperature is gradually decreases when it reaches the outside of the outer walls. But here in this case, in this problem we are taking now, it only just one material, one slab having thickness is equal to here L. It is receiving energy from the furnace or this air which is maintaining at higher temperature to the surface of the slab or the wall. That energy it may receive by using convection process or the radiation process. Then the heat energy flows from that is inner surface to the outer surface now, that is a length by using conduction process. After that the heat energy is dissipated by outside, that means generally it is environment, by using convection as well as the radiation process. So just we have to analyze the problem. So first of all, for receiving the energy by using radiations and convection process, and relieving the energy from the wall again by using conduction convection process, the energy flowing through the wall is determined by using Fourier's law of conduction. So that means by using conduction process. Okay, in these problems now we are taking now the slab. Assume T1 is representing the temperature at the inner surface which is maintained at higher temperature, and T2 is the temperature at the outer surface now. Let L be the that is thickness of the wall. According to the Fourier's law of conduction, so the amount of heat energy that is flowing through the wall is given by minus of K into A T1 minus T2 divided by L now. From this relation, so T1 minus T2 divided by, we can take it as L divided by K into A now. This is equation number 1 now, where Q is the heat flow, K is equal to thermal conductivity of the wall, A is equal to area of the cross section, L is equal to thickness of the wall, and T1 and T2 are representing the lower as well as the higher temperature of the given wall. Here composite walls now. Okay, in this case we are taking just 3 layers of the wall now. Let consider the wall or the composite slab made up of 3 different materials. Here represented as 1, 2 and 3. Having thermal conductivities K1, K2, K3 and their thickness represented as L1, L2 and L3 as shown in figure. One side of the wall is exposed to hot fluid now at this moment now. Having temperature TF and other side is atmospheric air which is maintained at temperature of Tn. The convective heat transfer coefficient between the hot fluid and the inside surface of the first wall, assume this is equal to H naught is the Hi, it is the convective heat transfer coefficient, and the heat which is transferred into the air from the outside the wall, assume this is nothing but H naught, it is representing that heat convective coefficient for the air when the heat is flowing through the air now. The temperature at inner and outer surface of the composite walls are T1 and T4. Assume this is nothing but temperature T1 at this moment. Here at T2, T3 and finally the T4 now. Whereas at the intersections of the constituent walls are T2 and T3 now. The heat transfer from hot fluid to the atmospheric air and involve the following steps now. When it is flowing here, hot fluid is there, but heat energy flowing to the air at the outer surfaces. This is between hot fluid as well as the air. It is having the slab which consists of 3 layers represented as 1, 2, 3. Here now, according to our previous discussion, the heat energy flows from the hot fluid to the this inner surface of the first block by using convection process. After that, the heat energy flows from block 1 to 2, 2 to 3 by using conduction process. After that, from 3 to again to the air, that is the atmospheric air, by using convection process. So here now we are taking the heat transfer of hot fluid to inside surface of the composite wall, that is by using convection process. That is Q is equal to K here Hi into A into T1 minus Tf minus T1 now, where Hi is representing convective heat transfer of hot fluid, A is the area of the cross section, Tf is representing the temperature of the hot fluid, and T1 is this inner temperature of the wall. From this relationship we got Tf minus T1 is equal to Q divided by Hi into A now. Similarly, for the first slab now, the heat transfer from inside surface to the second interface of the block now, that is between 1 and interface of 1 and 2, is given by Q is equal to K1 into A into T1 minus T2 divided by L1, where T1 is representing the temperature at the inner surface and T2 is the temperature at the interface of first and second block, and L is representing the thickness of the slab. From this relations again we can take it as Q is equal to K1 A divided by L1 equal to T1 minus T2 now. The heat transfer from the first interface, that is the interface of 1 and 2, to the interface of second and third is given by Q is equal to K2 into A into T2 minus T3 divided by L2 or Q by K2 into A divided by L2 is equal to T2 minus T3 now. I am taking this equation number 1, it is a 2, it is a 3 now. Similarly, the heat transfer from the second interface now, from this position to outside now, that is from T3 through T4, is obtained by using the relations K3 into A into T3 minus T4 divided by L3. From this relationship we got to Q divided by K3 into A divided by L3, which is equal to T3 minus T4. This is the equation number 4. Okay, finally, the heat transfer which is taking place from the outer surface of the outside the wall to the air by using convection process only. Hence, Q is equal to the amount of energy that is flowing to the air according to the convection process. Q is equal to H0 into A into T4 minus Tn. From this relationship we got to Q is equal to Q divided by H0 into A is equal to T4 minus T alpha, where T alpha is representing the air temperature which is outside of the wall now. That is at the fourth position now. This equation number is equal to, I am taking that 5. This is combining this equation 1, 2, 3 and 4. Finally, we got to, from the toward the right side, Tf minus T1 plus T1 minus T2 plus T2 minus T3 plus T3 minus T4 plus T4 minus T alpha. It is equal to Q into Q is the common word. A is also common now. Hence, the remaining values are 1 by Hi plus 1 by K1 divided by L1, 1 by K2 divided by L2, 1 by K2 divided by L3, 1 by K3 divided by L3, 1 by here H0. If A is nothing but if you take it is a common term. F A and other the Q now. Now from these relations now, here T1 plus minus both are get cancelled now. Again these two. Finally these are also get cancelled now. The remaining values is Tf minus T alpha, where Tf is representing the temperature of the hot fluid, which is toward the left side of the first block, and T alpha is representing the temperature of the air, the atmospheric air, which is toward the right side of the third block now. Okay, Tf minus T alpha is equal to Q into here now. Q is equal to, from this relation we got Tf minus T alpha divided by 1 by Hi into A, K1 into A into L1 plus K2 into L2 and so on, K3 by L3 into A plus H0 A now. So from these relations now, it can be written as now Q is equal to Tf minus T alpha divided by, here 1 by A is the common word we are taken now. The remaining values is 1 by Hi plus 1 by H0. The remaining values is that is if any number of blocks are there, that is sigma of n is equal to 1 to n is equal to n, that is Ln divided by Kn, where Ln is representing the thickness of the each block here now. Here Kn is representing thermal conductivity of each block now. So in these relations now, the magnitude of 1 by Hi plus 1 by H0 plus sigma of n is equal to 1 to n into Ln divided by Kn. This quantity is called overall heat transfer coefficient of the composite walls now. This is the important relations for the transfer of heat energy from the hot fluid to the atmospheric air when it is obstructed by the number of blocks now, or the wall is made up of so many layers. Okay, based on composite walls, we are taking one problem now. A slab of 0.2 meter thickness with thermal conductivity of 45 watts per meter per degree Kelvin receives heat from a furnace of 500 Kelvin, both by convection and radiations. The convection coefficient has a value of 50 watts per meter square per degree Kelvin. The surface temperature is 400 Kelvin on this side. The heat is transferred to the surroundings at T alpha 2 both by convection and radiations. The convection coefficient on this side being 60 watts per meter square per degree Kelvin. Determine the surrounding temperature. Assume F is equal to 1, where F is nothing but generally representing now, that is the shape factor now, which is given here 1 now. So first of all, we identify just here given data. A slab of 0.2 meter thickness. This is given L is equal to here 0.2 meters is given now. Here the slab is given now. See there, one side it is having hot fluid, the second side is having air now. That is, the heat energy is flowing from the hot fluid to the that solid here, which is represented here now. This by using convection as well as the radiation process according to these problems. Here the fluid is maintaining here 500 degree Kelvin, but while flowing, the inside temperature, the wall is maintaining at 400 degrees centigrade. That is, TF is equal to, according to these problems, 500 degree Kelvin, and T1 is equal to, that is 400 degree Kelvin is given. On this side, the heat is transferred to the surrounding set, it is given now. So based on these problems, this we have to determine the value of, that is, determine the surrounding temperature we have to determine. So first of all, here now, okay, the given data is the thickness of the slab, thermal conductivity of the materials, furnace temperature 500 degree Kelvin, convection coefficient to 50 watts now, surface temperature is equal to T1 is equal to 400 degree Kelvin is given now. The convection coefficient to H is equal to, for the hot fluid is given, for air is given 60 watts per meter square per degree Kelvin. Shape factor is equal to, assume just 1 for this radiation process. Let the surface temperature at T2 is equal to, here it is equal to T2. Here it is not given in the problems. And the surrounding temperature T alpha 2, here it is there now. So the temperature T alpha 1, here it is given, hot fluid temperature T1, the temperature at the inner surface, T2 at the outer surface, T alpha 2, air temperature. The surface area, assume it is equal to 1 now. For steady state conditions, that means the amount of heat energy flowing from the hot fluid to the block and the block to the air, that remains constant. So heat received by the wall by the radiation and the convection process is given by F into sigma into A T alpha 1 to the power of 4 minus T1 to the power of 4 plus H into T alpha 1 minus T1 now, where F is representing the shape factor. Generally, it depends upon the distance between the two materials in the case of solids now, as well as the, that is shape of the object. But in this case, we have taken F is equal to 1. Sigma is representing the, here the Boltzmann constant. This value is equal to 8.5 into 10 to the power of minus 8. And T alpha 1 is representing the temperature of the hot fluid. According to these problems, this value is given 500 degree Kelvin minus T1 to the power of 4. It is equal to T1 is equal to the temperature of the inner surface of the block, that is a slab, that is which is having contact with the hot fluid. According to the problem, this value is given 400 degree Kelvin plus H, that is for the convection process. H is representing coefficient of convective heat transfer, which is given here is the 50 values. T alpha 1 is representing the here now the temperature of the hot fluid. T1 is representing the temperature of the inner surface of the wall now. Substituting all the values in this equation, so we got that is 1.567 into 10 power minus 8 into 1 into 500 to the power of 4 minus 400 to the power of 4 plus 50 into here is given 500 minus 400. This value is equal to 7092.2 watts now. The amount of heat transfer through the slab is given by, that is by using the conduction process, K into A into T1 minus T2 divided by L, where T1 is the just inside temperature, T2 is the outside temperature of the wall now, which are given here now. 400 one is given. Second one is we have to determine. But since the rate of heat energy which is flowing remains constant now because the steady flow condition is given, hence this equation can be written as now 7092.2 is equal to 45 into 1 into 400 minus T2 divided by 0.2 now. From this relationship we can determine that the outside wall temperature T2 is equal to 368.243 degree Kelvin now. So on the other side of the slab, the heat energy which is there now, it is transferred to the air by using convections as well as the radiation process. Hence, the heat transfer from the wall is to the air is given by F into sigma into A, T to the power of 4 minus T alpha 2 to the power of 4 plus H into T2 minus T alpha 2 now. T2 already we determined this value is equal to 368.43 and substituting the values in these equations because Q is already given which is equal to 7092 which is equal to F is equal to 1, sigma is equal to 5.67 into 10 to the power of minus 8. Area of the cross section also we are assuming it is 1. So T2 is equal to 368.43 to the power of 4 minus T alpha to the power of 4 now. So we are getting just a quadratic equation in terms of T alpha 2 now, which is equal to 5.67 into 10 to the power of minus 8 T alpha to the power of 4 plus 50 into T alpha 2, which is equal to here 16,056 now. This is solving these equations by using T alpha 2 is equal to minus B plus or minus under root of that is B square minus 4AC, that is T alpha square minus 4 into A is equal to coefficient of alpha square value is given and substituting, that is generally it can be solved by the trial and error method only. This T alpha is equal to we got to 263.3 Kelvin now. This is our answer. Okay, these are the textbook I followed now. That is Sachdeva and Eunice Senegal, that heat transfer a practical approach. As well as some reference books also we taken. The authors of Goldman and C.P. Kodandaraman and Gosha Dasidhar. These 3 books we followed. Okay, thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.